in the last few lectures, we had been looking at the time domain approach to time series analysis. We have looked at the classical models and seen how we can estimate trend and seasonality. And then what we have looked at was, in general, how do you look at a stationary process? What is stationary? What is ergodicity? And why ergodicity is important and why stationarity is important to analyze a time series. We have looked at a very important tool, the autocovariance or autocorrelation function, which we use in the time domain analysis. What we will do today would be to look at very simple Box-Jenkins models. We will begin with the simplest of the Box-Jenkins model and go on and develop the ARIMA or the SARIMA models later in our studies. Before we do that, we will just be very quickly looking at what is meant by a deterministic or an indeterministic process, and then we will be looking at the MA and the AR processes, and we will be looking at only the simple cases. We will keep the more complex cases for later lectures. Before we begin with the Box-Jenkins models, let us look at what is meant by a deterministic or an indeterministic process. We say that the process is purely deterministic if the future values can be predicted without error. That is, if x t star is the predicted value of x t, then expectation of x t minus x t star square is equal to 0. This is the mean square error of prediction, and this is going to be 0. Now, this happens when we have a very nice curve. For example, if you have x t equal to cos twice pi t and there is no random component in it, then you give me a t value and I can give you the x t value precisely. We call such series as purely deterministic series. Obviously, you can see that from a statistical point of view, the purely deterministic series are not of great interest, because we do not really have to do much statistics about it, and there is no random variable involved that we have to take care of. As opposed to this, we have what is referred to as an indeterministic series. In this, the future cannot be wholly predicted from the past values, and usually expectation of x t minus x t square, that is the mean square error of prediction, would be tending to the variance of x t. Now, the larger the value of x t minus x t star square, the less deterministic it becomes. So, if this value is equal to the variance of x t, then we say that the process is purely indeterministic. But in most cases, we will be somewhere in between, that is, there will be some randomness and some part of it we can predict, and hence it will be somewhere intermediate between a purely deterministic and a purely indeterministic process. There is a very important theorem which is referred to as the Wolff's decomposition theorem. These days this is much more theoretical by nature, because we will be looking at primarily indeterministic series. It says that any discrete time stationary process can be expressed as the sum of two uncorrelated processes, one purely deterministic and the purely indeterministic. So, we can decompose any time series into two components, one purely deterministic and other purely indeterministic. Of course, there will be special cases like what we have defined already. You can have simply a purely deterministic process or simply a purely indeterministic process, but very often there is a combination of the two, and if you have an indeterministic process which is a combination of the two, we can segregate this into a purely deterministic and a purely indeterministic process. So, we can write x t as two components, where epsilon t or IID is 0 mean constant variance these are random variables, and hence this part is indeterministic, and omega t is purely deterministic with expectation of epsilon t and omega t is equal to 0. That is, the two parts are uncorrelated to each other. This is Wald's decomposition theorem, but in what we will be studying, we will be primarily concerned with indeterministic processes. So, anything deterministic we can always segregate out. The simplest of the indeterministic process is the purely random process. This is in fact the extreme of the indeterministic processes. What is a purely random process? Let x t be a collection of identically and independently distributed random variables which has mean equal to mu. So, they all have the same mu and they have the variance equal to sigma square. So, you can see that stationarity wise this would be stationary, the mean and the variance are independent of the time. Of course, we need to look at the correlation as well, and let us see what it is. We said it is identically and independently distributed. Now, gamma h therefore is equal to 0 for all h greater than 0, and we have rho h is equal to 1 if h is equal to 0, that is at the time point itself, and is equal to 0 otherwise. We call this a purely random process. So, how does the correlogram look like? The correlogram, this is a single spike at h equal to 0, and otherwise all the other values are 0, and hence it coincides with the h axis everywhere else. It is the simplest of the purely indeterministic process. There is no deterministic term in this. Now, if mu equal to 0, this is a very special case, the process x t is generally referred to as white noise. This is an engineering term, and this has become a very common term that we use in statistics also. And usually we would be denoting epsilon t as Wn 0 sigma square. So, when we write Wn 0 sigma square, we mean that the process is a white noise, that is, it is identically and independently distributed epsilon t's with 0 mean and variance sigma square. If you look at the condition, it really is the condition that we generally have for errors in general statistical studies like regression. So, white noise would be a fundamental process that we would be using several times as we go along in more complicated models. The moving average process. So, this is again one of the simpler process, and we say we have a moving average model of order q if x t is equal to beta naught epsilon t plus beta 1 epsilon t minus 1 plus beta q epsilon t minus q, where epsilon t's are the white noises and beta j's are the parameters of the process. Usually we take beta naught equal to 1, so that the current time white noise basically has a coefficient of 1. So, if you look at x t now, what we have is that x t is a linear combination of this white noise of the current time white noise and the past white noises, okay, past q white noises. So, we call it a moving average process. Obviously, since all the epsilon t's have 0 mean, expectation of x t is going to be equal to 0. What about the variance? Since epsilon t's are independent, the variance would translate to the sum of the variances. So, we have the variances as beta j square variance of epsilon t, which is equal to sigma square, and the sigma square comes out as a constant, and we have this as sigma square into summation of beta j square summing from 0 to q. The autocorrelation. Now, we have the autocorrelation as sigma square summation of j equal to 0 to q minus h beta j plus h, as long as h is less than q. If h exceeds q, then you see x t and x t plus h. X t is composed of epsilon t minus 1, epsilon t minus q. X t plus h is composed of epsilon t plus h minus 1 up to epsilon t plus h minus q. But since h minus q is greater than 0, so epsilon t minus h plus q would be greater than epsilon t, and hence the two series will have no common epsilon t's, and hence when you take the expectation, since the epsilon t's are uncorrelated, it will become 0. So, for all h greater than q, gamma h becomes 0, and we can collect the coefficient and show that it is equal to beta j plus h summed over j into sigma square if h is less than equal to q. And now it is easy to get the autocorrelation function, which is rho h. You just divide the gamma h by gamma naught and you get the autocorrelation function, which becomes 1 if h is equal to 0, it's 0 if h is greater than q, and this becomes a ratio of the covariance gamma h by gamma naught if h is less than equal to q. How does the correlogram look like? The correlogram would be starting at 1 when we have h equal to 0, and then it would oscillate, or it will depend on what the parameters is like. It might not be going below 0 if all the parameters are positive. So, there may be some oscillation, but the important thing is that it will get damped, and then it will coincide with the h axis as soon as you cross the q value. So, for any gamma or rho having a h value greater than q, you have a value of 0. In this case, we have taken the order to be equal to 8. So, up to 8 the value is non-zero. From 9 onwards, whatever value you take, the value becomes 0, and therefore, it will coincide with the h axis. So, this we will see is a good way of identifying the order of the moving average process, because it becomes 0 as soon as you exceed the order of the process. So, as I said, it oscillates between 0 1 depending on the beta j's, and it becomes 0 beyond the point q. These are two features that we should keep in mind. As a special case, we have a simple unweighted moving average. What is an unweighted moving average? If we take beta j is equal to 1 by q plus 1 for all j equal to 0 to q. Remember, x t is a combination of past and q past and one current value. So, there are q plus 1 epsilon t's. If all of them has the same weight, that is 1 by q plus 1, then we say that it is a simple unweighted moving average. And in that case, the rho h turns out to be 1 minus h by q plus 1 if h is less than equal to q, but greater than 0. It is 1 at 0 and is 0 if h is greater than q. And you can see that this is basically a linearly decreasing function of h, and the correlogram would look like this. So, it will, in this case, we have taken the q value to be 10, to be 9 in fact, and at 10 it coincides with the h axis, and beyond 10 it will go along the, it will not dip below the 0 line, it will go along the 0 line henceforth. So, this is a very special case where we have a straight line correlogram. Now, let us look at the other more common process, the autoregressive process, and this is much more intuitive than the moving average process. An autoregressive process of order p or ARP is defined as xt is equal to alpha 1 xt minus 1 plus alpha 2 xt minus 2 plus alpha p xt minus p plus epsilon t. So, we have a lag of order p of the same sequence. So, xt depends on its own past values up to a lag of order p. We call it an autoregressive process of order p. Again, the epsilon t acts as the error here, and epsilon t's are white noise with which is 0 mean variance sigma square, and alpha j's are the parameters of the process. Unlike the AV process, which is explained by current and past values of the innovations, epsilon t's, we very often call the epsilon t's innovations as well. You can call it errors, you can call it white noise, you can call it innovations. The AR process has its own past values as the regressors. We will look at a very special case of the AR value in today's class, and we will discuss AR process more generally in subsequent classes. Let us look at the special case of p equal to 1. The AR process xt is equal to alpha xt minus 1 plus epsilon t. Notice that I have just dropped alpha 1 because you just have a single alpha, so you can just call it alpha xt minus 1 plus epsilon t. Now, if we have an infinite number of past values, we can write xt as summation of the innovations or the white noise of an infinite number of past values. This we can do by, if you have xt equal to alpha xt minus 1 plus epsilon t and you replace xt minus 1 by its past values, xt minus 1 is alpha xt minus 2 plus epsilon t minus 1. If you go on doing this, you can write the whole thing in terms of the epsilons, and that is the sequence that we get here. And if you look at this, it is very easy to see that since epsilon t has 0 mean, xt's must have 0 mean. What about the variance? The variance would be alpha to the power of twice j sigma square summed over j, because the epsilon t's are 0 mean. And if you take sigma square out, then it is sigma square into summation over j alpha to the power of 2j. And if alpha is less than 1, you know that this is a geometric series and it will sum up to 1 by 1 minus alpha square. So, the variance comes out to be sigma square by 1 minus alpha square, of course, provided the absolute value of alpha is less than 1. What about the autocovariance function? If we use the same argument as we did for the variance, we can show that because xt and xt plus h should have a difference of 8 steps. So, we have a alpha h which should be coming out, and then we should simplify to gamma h equal to sigma square alpha to the power of h 1 minus alpha square for alpha less than 1. Of course, if h is negative, we take the modulus of that. Therefore, rho h is equal to alpha to the power of h. You divide this by the divide gamma h by gamma naught and you get the rho h value. So, rho h value becomes asymptotic to the h axis, but never equals it. So, as you go on increasing h, because alpha is less than 1, this will become smaller and smaller, but it will never be equal to 0. And if you have minus 1 less than alpha less than 0, then rho h is a damped oscillation. So, if you have alpha which is positive, it will stay above the h axis. If you have an alpha value which is negative, then it will be oscillating around the h axis. It will be damped, but it will never coincide with the h axis itself. So, the correlogram would look somewhat like this. Now, note that for a finite lag, what we have is the covariance xt plus h, as I said, would be equal to alpha to the power of twice t minus 1 by alpha square minus 1 into alpha h and sigma square, and you can see that this is a function of t. So, in general AR process is not stationary. What we saw in the last slide was that this AR process is stationary because we had the condition that alpha is less than 1 in absolute value, and hence this would be tending to 0 for large t. So, this for stationarity we need the condition that modulus of alpha is less than 1, and then we can write the process in terms of the infinite past innovations, and we can show that this would be converging to a finite quantity which would be independent of the time point that we are in. So, in general, remember, unlike the moving average process, the AR process is not stationary, and it is only stationary if the alpha value has an absolute value of less than 1. Let us very quickly look through one special case. Take alpha equal to 1, which violates the stationarity condition, mind you, and let us see what happens here. We have x t is equal to x t minus 1 plus epsilon t, because alpha is equal to 1, and this you know is a random walk. And if we replace x t minus 1 on the right hand side by x t minus 2 plus epsilon t minus 2, and if we go on doing that, then we can write x t as epsilon t plus epsilon t minus 1 up to epsilon 1. And then if we take expectation, it is going to be 0. So, expectation wise we will not have a problem, but if you take the variance, it will be t times, because there are t terms there, and each of them will contribute sigma square to the variance, there it will be t sigma square, and similarly for gamma h it will be t sigma square. So, the process you can see is not stationary. The variance and the autocovariances depend on t. So, in general, as I said, alpha less than 1 in absolute terms is a necessity for stationarity, and you can see even if alpha is equal to 1, then we do not have a stationary autoregressive process. Interestingly, if you look at the random walk, if we take x t minus 1 to the left hand side, we have x t minus 1, which is basically the difference of x t. So, delta x t is x t minus 1, and it is equal to epsilon t, and epsilon t is white noise and hence stationary. So, we can see that the first difference is stationary. Remember, we had in our classical model said that differencing can often reduce a model to a detrended, deseasonalized, or to a stationary model, and this is one example where we can have stationarity by differencing a non-stationary sequence. Today we had been looking at the Box-Jenkins model. We started by looking at what is meant by a deterministic as opposed to an indeterministic process. Now, in general we will be concerned more with the indeterministic processes, either pure or just the general form of the indeterministic process. We have looked at the Wahl's decomposition theorem, which actually separates the deterministic and the indeterministic parts. And while looking at the indeterministic processes, we started with the purely random process, which is possibly the most simple of the processes, and then we had moved on to the moving average process and the autoregressive process. We have studied in slightly more detail the autoregressive process of order 1. In subsequent classes, we will be looking at the autoregressive process of general order, that is of order p. We will also be moving back to the moving average process. There are certain concepts that we will be looking at over again for the moving average as well, and then we will move on to the general ARMA and subsequently the ARIMA models.